it's a fight between sodium wanting the electrons and water. So if it's a water solution, it's a fight between sodium and water. And I have to tell you that it turns out water wins out. So sodium is not going to pick the electrons, water is going to pick it up. And if you look inside the chart, you'll see the half reaction. So again, that would be given to you, not expected to know that. Now take a close look at that water solution reaction and notice it actually forms hydroxide ions. That's why the question asks you for pH. Okay, now let's look at what I think would be the attack on this. We're trying to get pH, and obviously if we're going to get hydroxide ions, we would have to get POH first. And what is POH? It's an abbreviation for the hydroxide ion concentration. Okay, now what's the definition of that bracket? What's molarity of hydroxide? It would be moles of hydroxide per liter. Sorry for my little typo here, that should be a little higher. So moles of hydroxide ion per liter. But we don't have liters, we have 50 milliliters. So what we're going to do is we're going to convert moles of hydroxide per 50 milliliters into moles per liter using the conversion factor that 1,000 milliliters equals 1 liter. So I hope out of this analysis you see the missing information is moles of hydroxide. So I'm going to give you a moment now on your own to see if you can convert the information given to you into moles of hydroxide, because if we can get that, maybe we can get pH. So look at the information given. I'll analyze it with you. So first of all, you're given amps. Now amps is a 2-line piece of information, so I don't think that's a good start to you. 1,000 seconds. That is a potential 1-line beginning. 50 milliliters. Now we're going to use that later to get the molarity. Yeah. So I hope you agree that 1,000 seconds is the starting point. So let me give you a few moments on your own. See if you can convert 1,000 seconds into moles of hydroxide. Okay, so I start off with 1,000 seconds. Then I use the amperage as a conversion factor. So there's 0.0965 coulombs per second. Okay. Now the next conversion factor I screwed up. I left off the units. So why don't you put, where it says 96,500, why don't you put a little C next to that, squeeze it in for coulombs. Should be right there. Okay, I screwed up. So 96,500 coulombs would cancel it out and get you 1 Faraday. And then look at the balance equation. It says that 2 Faradays, 2 moles of electrons, are needed to form 2 moles of hydroxide. Now, obviously, you could reduce that down to 1 to 1, but I just thought I'd be consistent and just write the numbers that are in the balance equation. Okay, now I got an answer of 1 times 10 to minus 3 moles of hydroxide. I don't believe it, so let me try it on my calculator. So 1,000 times 0.0965 divided by Faraday's constant times, that ought to be it. Okay, yeah, I got an answer of 0.001, which is same as 1 times 10 to minus 3. Okay, look at the bottom line now. So I took the moles of hydroxide per 50 milliliters. Where'd the 50 coming from again? That was given in the problem. Okay, so we have to get to molarity. So we don't want moles per milliliter, we want moles per liter. So now I throw in the conversion factor to 1,000 milliliters equals 1 liter. So I guess I'm supposed to divide my answer by, multiply by 1,000. So times, I should have divided by 1,000. So let's see. Let me do it again. That's coming out too well. Give me time. So 1 E3 minus divided by 50. I think that's what I forgot. Divided by 50 and then times 1,000. Okay, so I get an answer of the molarity is 2 times 10 to the minus 2 molar. Abby, do you concur?
Yes.
Okay, now that's the hydroxide, so I'll take minus the log of that. So I get a POH of 1.69, and then I'll subtract it from 14, and I get a pH of 12.3. Now, you are looking at the most modern way to chlorinate a swimming pool. Now, a few years ago when I did have a swimming pool, I invested in this. And what happens is you put salt in your swimming pool. So you need a salt water solution. Then by the pump, you have a power supply that puts electricity in the water. And what happens is the left-hand reaction takes place, so it makes chlorine gas. The thing I didn't like about this process is, look at the right-hand side. Darn it, it's making hydroxide ions. It's making the swimming pool water basic all the time, so it's messing up the pH. So about once a week, I have to pour some muriatic acid in there. So it's very disturbing. Now, this really bothered me until I came across something interesting. Look at the bottom thing I have on here. It turns out the chlorine, which you're making, reacts with hydroxide to make HClO. And you might recall HClO is actually the active ingredient. I just lost it somehow. Anyway, HClO is a chemical that actually kills the bacteria in the swimming pool. Okay, I want to do two more problems with you now. And the reason I pick these is because these are two where I want you to be able to figure out the half reactions on your own. So they're not really hard, but that's the kind of thing I want you to do. So you're seeing too much. Okay, right here. Okay, so here's a problem I want to do with you. Okay, you're seeing too much. Don't look. Okay, so here's the reaction. Here's the problem I want to do with you. From a solution of copper chloride, how many minutes will it take to plate out 2.25 grams of copper at a current of 7.8 amps? So what I want you to do first of all, and this is the part I expect you to do on your own because it's really not that hard, see if you can write the half reactions taking place there. So notice you're starting with copper chloride and you're trying to produce pure copper. Remember, a half reaction always has to have electrons in it, so see if you can figure out what the electrons are going to be. Okay, time's up. Let's see how you're doing. Okay, so first of all, copper chloride, you must have, let's see, using the rules of priority, chlorine would have priority, and chlorine would be a -1. There's two of them, so the copper must be +2. Okay, so this half reaction would be the copper +2 and the copper chloride is going to react with electrons to form copper 0. Now to be balanced, would you agree it has to have 2 electrons? So that's the part I expect you to be able to do on your own on the exam. Okay, so I'll give you something like this, and hopefully you can handle it. Okay, next thing you have to do is, what's the mathematical setup for this problem? Okay, so let me give you a moment on your own now to see if you can solve this problem. Now, notice you're asked for a one-line ending, how many minutes? So look at the information given to you and decide what would be the one-line beginning. And then your goal is to use clever conversion factors to finally get to time in minutes. Okay, hopefully you're set up okay, so let's see if you agree with me. Okay, first of all, the only one-line beginning you have is the 2.24 grams of copper. Now what about the amps? Well, that's really a two-line piece of information. Remember, that's coulombs per second. And usually it uses a conversion factor later in the problem. So I started off with the 2.2 grams of the copper. Okay, and then I use the conversion factor of the atomic weight of copper, 63.5. Hopefully you have a periodic table available to you. So I converted from grams of copper into moles. Okay. Okay. Now once you have the material in moles, here's your golden opportunity to use the half reaction. So notice the half reaction says that 1 mole of copper would require 2 moles of electrons, 2 Faradays, to do the job. Okay, so we now are at electricity. We now have Faradays. Okay, now how can you make progress? Next conversion factor, cancel out the Faradays and get to the electricity. That would be the coulombs of charge, 96,500 coulombs of charge. Okay, now here's you want to use a, wait a minute, I think I made a mistake. Amps is coulombs per second, but I need coulombs on the bottom. Amps has coulombs on the top. What should I do? Just kidding. Yeah, you can flip a conversion factor any you want to. So to cancel out the coulombs, I need the 7.8 coulombs on the bottom, and seconds would be on the top. Now you'd be done. We now have time, except Berg wanted minutes, so the last conversion factor would be that 60 seconds equals a minute. Okay, I got an answer of 14.6 when I did this midnight last night. Let's see if I can duplicate it. Please check me out on your calculator. So 2.25. Okay, and that gets divided by the atomic weight, so divided by 63.5. And that gets multiplied by 2. and that gets multiplied by Faraday's constant, and I got an answer of 14.6 minutes. So here's the last problem of the semester. Okay, from a solution of sodium chloride, so you have a sodium chloride solution, what amperage, I want to solve for current now, is needed to produce 100 grams of sodium metal in 1 hour? Now I want you to do two things before we look at the solution. Write down the balanced half reaction. That's the critical hard part for you. And also I want you to write down the units for the answer. So hint, you're starting with sodium chloride and you're trying to make sodium. So what would be the balanced half reaction in that case? And Berg wants you to solve for amperage. And so you need to know what the units are for amperage. Okay, time is up. Let's see how we're doing. Okay, do you agree? Is that the balanced half reaction? So sodium chloride would have sodium ions in it. And as far as its oxidation state, you can get it off the periodic table, or actually I think sodium is on the rules of priority as one of the top ones. Okay, and so you need 1 E minus to write a balanced half reaction, and amperage has units of coulombs per second. Now notice this is a weird problem because Berg wants a 2-line ending, coulombs per second. With the conversion factor method, if you want a 2-line ending, you need a 2-line beginning. Look at the information. Berg did not give you a 2-line beginning. Well, sometimes you have to make up your own 2-line beginning. What do you think? You're only giving two pieces of information. So here's what I decided to use. So my 2-line beginning is, I decided to put the 100 grams of sodium over hours. Now, how did I know to arrange them in that way? I could have put 1 hour on the top and 100 grams on the bottom. Well, look at our goal. We're trying to get coulombs per second. So I do want time on the bottom. Okay, now there's two things we have to do. We have to convert grams somehow to coulombs. I have no idea how we're going to do that. And hours to seconds. So it's like two separate problems in one. Let's just focus our attention on the grams of sodium and see what we can do. So the first conversion factor, I thought it'd be a good idea to convert grams of sodium into moles. That seems to be progress in chemistry. Now, moles is always a good thing to get in chemistry. Okay. Then next conversion factor, I then converted 1 mole of sodium into 1 Faraday. Where in the heck did you get that conversion factor? Look at the balanced half reaction. It says 1 mole of sodium requires 1 electron, 1 Faraday. Now, what if the balance equation said Na plus 2 electrons? Then it would be 1 mole of sodium required 2 moles of electrons, but it's 1 to 1. Okay. Now, from Faraday's, I'm going to use Faraday's constant. 1 Faraday is equal to 96,500 coulombs. Now, why did I want to use that one? Because that's the top half in amperage. I now have coulombs on the top. So I'm done with half the problem. Now go back to the beginning. I now have 1 hour. Let's work on converting that to seconds. So I have the conversion factor here. So 1 hour is equal to 60 seconds. So notice that would cancel out hours on the bottom, hours on the top. And then I will convert 60 seconds to a minute. And I got an answer last night of 117, but I was tired. I forgot to write the units. So you write it in, please. The units on the answer should be minutes. Okay, now let's see if I did it correct. I'm going to try this on my
The units would be coulombs per second, right?
No, the units would be, let's see, we're left with coulombs and seconds. Yeah, so coulombs per second, right? Thank you. So let's see if I can get the right answer. So I start off with 100. And let's see, that is going to be divided by 23. And that's going to be multiplied by Faraday's constant. And that gets divided by 60 twice. And I got an answer of 116.5, which rounded off to 117 coulombs per second. Okay, now pronounce you experts on coulombs, on Faraday's problems. So here's some homework problems from the book so you can practice these.